Okay, this is the video lecture for Math 181. This is the second part of the video lecture for Thursday, April 16th. And the topic again is the definite integral. And if you guys recall from the first part, we were in the midst of doing an example problem. And in part A, we actually calculated the approximate area under this curve for the interval 0 to 2. We calculated that area approximation by using 4 rectangles and adding up the areas of the rectangles. In part B, we're going to evaluate the definite integral from 0 to 2 of x squared minus 2x. So what we're going to do here is we're going to evaluate this integral by taking the limit as n goes to infinity of our Riemann sum. So we're not going to get an approximate area under the curve here, we're going to get an exact area. And recall that the definition of a definite integral is defined as the limit as n approaches infinity of the Riemann sum from I equals 1 to n of f of x sub I times delta x. This is the height of our rectangle, this is the width of a rectangle. We're summing up all the rectangles and taking the limit as n goes to infinity. Okay, the first thing to do here is we want to talk about what is the width of our rectangles. Well, the width of our rectangles is the two endpoints, 2 minus 0 divided by n. We're using n rectangles. And this comes out to 2 over n. So that's the width of our rectangles. And then the next thing we're interested in is what are the different points at which we'll evaluate our rectangles. Well, x sub 0 is 0, okay, because that's the left endpoint of our interval. X sub 1 is 2 over n, okay. X sub 2 is 4 over n. X sub 3 is 6 over n. These are the various, we're dividing our interval up, and these are the various points at which we're going to determine the height of our rectangles. And if you guys see, we can generalize this to x sub I. X sub I, so the ith point along this interval from 0 to 2 is equal to 2I over n, okay? And what we're going to do now is evaluate the sum. And so I can rewrite the sum as limit as n approaches infinity of the sum of I equals 1 to n of f evaluated at our x sub i's, which we found in this case is 2I over n, times the width of the rectangles, which is 2 over n. Okay, and now what I can do is I'm going to use some algebra to simplify this sum. First of all, I'm going to pull this 2 over n, this width, in front of the summation sign, because this does not depend on I. Since this does not depend on I can't pull it out from the limit because the limit depends on n, but I can pull it out from the sum because the sum just depends on I. So this turns into the limit as n approaches infinity of 2 over n, okay, times the sum from I equals 1 to n. And now, and I get f of 2I over n. And then now what I'm going to do is I'm going to use this functional form here. So I'm going to rewrite this as the limit as n approaches infinity of 2 over n. And now I'm going to actually plug in my function. So this f, so my function f is x squared minus 2x. So basically what this turns into is the sum I equals 1 to n of x squared, which is 2I over n. I'm plugging in 2I over n into x squared. So I get 2I over n squared minus the sum from I equals 1 to n of 2 times 2I over n. Okay? And with a bracket there. Okay? So I'm basically plugging this 2I over n into my function. And I'm going to now try to simplify this sum. And so this sum equals the limit as n approaches infinity of 2 over n. And then I'm going to evaluate this sum. And if I do that, I get, I'm going to first tackle this sum. I can pull out, so this turns into the sum. Let me rewrite, won't skip a step here. This turns into the sum I equals 1 to n of 4 of 2 squared over n squared times I squared minus the sum of I equals 1 to n of, now here we have, I can pull this 2 out, I pull the 2 out, then I get another 2, I get 2 over n times I, okay? And now what I can do is I can pull out anything that doesn't depend on I. I can pull it out of this sum. Now this kind of algebra might seem a little confusing to you guys. I encourage you guys to watch this video maybe twice. Take a look at the textbook. It has a good treatment of this. Because I realize you might be thinking, what the heck's going on here? But this is just algebra. So what I'm going to do now is I can pull this term. I can pull this term in front of the summation sign because there's no I dependence. So here I get 4 over n squared times the sum of I squared from I equals 1 to n. Minus, I can pull out this 2n, so I get a minus 4 over n times the sum from I equals 1 to n of I. So this is now what I get. And now I can use those earlier formulas for the sum of I squared. So this now equals limit as n approaches infinity of 2 over n times 4 over n squared. And then the sum of I squared, if you guys recall, the sum of I squared was n from I equals 1 to n was n times n plus 1 times 2n plus 1, all divided by 6, okay? Then over here I have 4 over n. If you guys remember, the sum of I from I equals 1 to n was n times n plus 1 over 2, okay? And again, these formulas, I just give these to you guys. So anyway, I'm going to evaluate this now. And what I want to do is think about in the limit as n goes to infinity, n plus 1, the limit of n plus 1 goes to n. Let me rewrite this. It's going to be a bit confusing here. In the limit as n, says the limit as n goes to infinity, n plus 1 goes to n. And 2n plus 1 becomes 2n. Because as n becomes very large, the 1 here becomes insignificant. N plus 1 turns into n. And the 1 here becomes insignificant. This turns into 2n. So I'm going to use that fact. We get 2 over n. Here we get 4 over n squared. And here this turns into n. This turns into an n. This turns into a 2n divided by 6 minus 4 over n times n over 2. Okay, and now we're almost there. I know it's a lot of algebra, but let's put all our n's together. This becomes limit as n goes to infinity. And let's multiply all these n's together. So here I'm going to get a 2 times a 4 times a 2. So that turns into 16, right? 16 n cubed over 6 n cubed. And then over here I get 4 times 2 is 8, and I get 8n squared. 8n squared divided by n times 2, right? That's 2n squared. Okay, I'm almost there now. And now these n's cancel, and these n's cancel. And this now becomes, there's no more n's here, and this becomes 16 over 6 minus 8 over 2, which equals 8 over 8 thirds minus 4. Okay, and what does that come out to? Well, this comes out to minus 1.33, repeating. Okay, that's a lot of algebra. But anyway, the point is, this is now the area under this curve in the interval 0 to 2. Okay, this is not the approximate area, this is the exact area. So what we've done is we've taken the definite integral here. The definite integral is equal to the limit as n approaches infinity of the Riemann sum of these rectangles. And then what we did is we did some algebra. We figured out the width of our rectangles. We figured out the points at which we evaluate the height of our rectangles. We plugged all this into this summation sign. And then we used some algebra and some formulas for summations of I squared and I. And we came out with this area. This is exactly correct. Okay? This is exact. And that's pretty cool. What we got in part B, we got minus 1.25. This was approximate. So our approximation in part A was pretty good, but not exactly true. So this is the exact area under the curve. Now, if this seems like a lot of work to you guys, the good news is no one in calculus actually does a definite integral this way, by doing a Riemann sum. There's a much simpler shortcut to doing these integrals, which we'll talk about in a little bit. But this is the truly pure way, true form way to do this integral. Okay, let me just talk about one more thing here before we go. And we're going to talk about some properties of definite integrals. So here are some important properties I'm going to write down for you guys of definite integrals. Properties. Okay, one property is if you integrate from a to a of f of x dx, if your limits are the same, this equals 0. Another important property is the limit from a to b of f of x dx equals negative. If you switch the limits, you get a negative here. So the integral from a to b of f of x equals a negative of b to a of f of x. Another important property is if you have the integral from a to b of some constant c dx. So if your function is a constant, this just equals the constant c times b minus a. Okay, another important property is the integral from, if you have a constant here, a to b of a constant times f of x dx. You can always pull constants out from an integration sign, and you get the integral from a to b of f of x dx. And let's see, is there one more property that I want to give you guys? If you have the integral from a to b of the sum of two functions, f of x plus or minus g of x dx, you can always break this into two integrals. So this is a to b of f of x dx plus or minus the integral from a to b of g of x dx. You can always break your integral into two pieces. Let's just review these. If you're integrating from a to a, in other words, you have no interval, the integral is 0 because there's no region under which you're trying to find an area. The interval is 0. You can always switch your limits, flip your limits, and it gives you a minus sign. If you have the integral of a constant, if your function is a constant, it's always equal to the constant times the width of the interval. If you have the integral of a constant times the function, you can always pull the constant out from the integral sign. And then finally, if you have the integral of two functions added together or subtracted, you can always split this into two different integrals. Okay, that concludes part 2 of this video lecture. I know that got kind of messy with the algebra in that previous problem, but just take a look at it and we can do a practice problem for you guys on Thursday. Thanks.